Welcome. Let me introduce Wolfram Barfuss from University of Bonn, who's been doing cooperative evolutionary dynamics. Yeah, please welcome.
Thank you very much for the invitation. It's a pleasure to be here. I trust you can see my slides.
Yeah, absolutely.
Wonderful. So, are we smart enough for the good life? That's the sort of slightly perhaps provocative title I chose. And in this talk, I want to talk about what collective learning dynamics is, why we need it, and what we can do with it for what I'm increasingly thinking about the joint analysis of so-called human-machine ecologies. So let's get right into it. I structured it in 3 parts. First, addressing why we need this, looking at the challenge of collective action in human-machine ecologies. Then how we can do something about it by building bridges between complex system science and multi-agent learning. And then sort of as a concrete case study example in the results and what section, I'll show you how we can apply this in a concrete study, asking how do natural tipping dynamics affect sustainable collective action. And here I'm drawing upon basically 2 papers. One, Collective Cooperative Intelligence, is a perspective piece with many insights from different authors. And then the more concrete study appeared recently in ecological economics. So let's start with why. So I think really the good life for all within a healthy planet is the challenge of the 21st century. And the question is, are we smart enough to get there? Are we smart enough for the good life? And to me, this is sort of a joint analysis.
Second?
Can I turn the power off?
Although we don't have Wi-Fi at all.
Greg, maybe you need to mute. Oh yeah, wonderful. So when I say human-machine ecologies, to me, that's sort of the joint analysis of 3 interrelated questions. First, what makes a society just? So a millennial-old question. But perhaps the intelligence angle can give us a new perspective. What kind of intelligence is required to get there? Then on the ecology side, drawing upon and touching upon ecological and environmental sustainability issues here depicted by the planetary boundaries, highlighting it's not just about climate. There are other dimensions like biodiversity, oceans, land. And there, to me, there is this surprising question that it exists at all. Why and when do intelligent actors threaten their own life support system, as we might do at the moment? And then in the middle, we come to the machine with artificial intelligence, but understood very broadly. When is a superintelligence aligned with a safe and just society? And so the goal here is really, we want to get in a safe, ecologically safe, socially just, and intelligently aligned space. Here, advancing the so-called donut by Kate Raworth, the safe and just space with the alignment dimension. So how do we get in there? And I think what is without dispute is we need collective action, we need large-scale collective action, and we need fast, so urgent large-scale collective action. How do we do that? How do we get there? So as you know, the scientific community, we analyze the dangers, we write reports about the threats we are facing. We propose solutions, how to decarbonize rapidly, for example. And these 2 activities seem to underlie, based on a model of collective decision-making that works approximately like that. You know we have a problem, we know what we can do about it. So if the information is there and the actions are set, why are we not acting more? And so in my research, asking basically, maybe we have the wrong model of collective action. It's not that simple. And of course, The challenge of collective action is broadly addressed under the research around cooperation. So when I say cooperation, I mean in the very simplest model, an individual pays a cost C such that everyone in the collective, everyone in the group receives a benefit. And this sort of can induce a conflict of interests between individual interests and collective interests. So here you see a typical payoff or reward matrix known under the prisoner's dilemma, but the basic idea is, let's say we play a game, we both can either cooperate or defect. And so no matter what you do, I'm always better off defecting. So when you cooperate, the greed to exploit you drives me to defection, because here 5 is larger than 1. But when you defect, it's the same, because I fear of being exploited by you. 0 is greater than -2. But the situation is the same for you. The game is symmetric. So individually, you want to defect. But collectively, we would be better off if we would cooperate. So having a 1 of utility is better than a 0. And so the common solution is we need outside authorities that regulate, or we need to privatize. And then we can avoid that dilemma. Problem there is this is not always possible. And this same structural problem also extends to machines under the umbrella of cooperative AI here in this comment from 2021. To help humanity solve the fundamental problem of cooperation, scientists need to reconceive artificial intelligence as deeply social. However, it's not at all that the commons have to be a tragedy all the time. Here, drawing upon research by Eleanor Ostrom and colleagues, the tragedy is not inevitable. Things are not as simple as they seem in the prototypical model, and human motivation is complex, and the resource systems themselves have dynamics that influence the response to human use. Centralized authorities tend to overuse the commons as well. And so she's pioneering this solution approach of bottom-up approaches, decentralized governance, and cooperation through social reciprocity. And if we extend this to our very simple model of the 2 dimensions of cooperation and defection, we can actually make up a space of fear and greed. So if both fear and greed are present, we have a prisoner's dilemma. But when only greed and no fear, we have a so-called chicken game, where the asymmetric equilibria are the asymmetric pure strategies are the equilibria. When there is only fear but no greed, we have a coordination or stack-hand game. And if we remove fear and greed, we can be, or we sort of are in a harmony. There's no conflict of interest between individual and collective anymore. Regardless of what the other is doing, everyone wants to cooperate and is happy there. So this is already, a space mapping up of these simple fear and greed dimensions. However, the problem is that this seems to also not be the end of the story. It's still difficult to scale this approach up, especially on the global level. If we have anonymous participants, if we have a vast amount of actors, then the cooperation problem is not resolved. So the challenge there, or what are the challenge areas that we need to tackle, maybe to rephrase that, are we smart about the good life in a more slightly scientific term, perhaps? Can many actors, each learning from their own experience and pursuing their own interests, still reach a good joint outcome? And so just to be able to answer that question, we thought, okay, we need to get a modeling framework, basically, a transparent, coherent modeling framework that allows us to connect the individual in different environmental contexts, the cognitive agency within them, the emergent collective behavior upon them, and all of that in a dynamic fashion. Because many of the quantities we are interested, like resilience, stability, are rooted in dynamics. So how do we get there? And the basic punch is we bridge complex system science and multi-agent reinforcement learning to have sort of a merger that I'd like to call collective learning dynamics. So if we take a step back and just ask, how could we model something like that? What are typical modeling traditions? Let me make up this space of, three modeling traditions of dynamic system models, very much used in complex system science, coming from physics, biology, things like natural science. We have equilibrium-based models, very important in economics, where the equilibrium is always the place that fulfills a goal, a target function. And then agent-based models, sort of a hybrid. You could view multi-agent reinforcement learning also as some kind of agent-based model, but also very prominent in complexity science. So, and if we now look about our model desiderata, like the transparent, coherent account of the dynamics of collective behavior emerging from individual agency in different environmental contexts, then we have to assess that none of them out of the box, if you just take the standard approach, fulfills all of them. Dynamic system models do not have a natural way to think about agency. Equilibrium-based models are most of all static, and often because of that assume sort of hyper-rational type of agency. And agent-based models are sort of super flexible, but maybe that flexibility is also problematic because it's not clear, how knowledge can accumulate through agent-based modeling. So I don't have anything against any of these traditions. It's just me reporting of what I thought, okay, neither of these approaches is the absolute right fit in the form, I got used to. So because of that flexibility, agent-based modeling can often be a bit opaque. So how do we go about it? Well, we have complex system science as a tradition and multi-agent reinforcement learning as a field. Complex system science is very insightful. It produced a rich understanding of how cooperation can emerge. And I'll give you an example of that in a minute. Problem with it, it tends to be a bit simplistic, ignoring individual level complexity and the environmental context. Multi-agent reinforcement learning, on the other hand, is a very rich framework. It combines the collectives of individually intelligent agents in dynamic changing environments. We can model a lot of things there. But the problem is, on the algorithmic level, it can be hard to understand, a bit obscure. It's highly stochastic, computationally expensive, and therefore challenging to interpret. So let's give an example of complex system science. And of course, this is a rich field, but here I use the famous 5 rules for the evolution of cooperation, this nice summary paper by Martin Nowak. The individual rules are not as critical for now as maybe more the form as they are presented. So you see here different sort of mathematically analytical conditions when these are stable, when these are sort of viable solutions, and also look at they all have some kind of social aspect in some direct reciprocity, indirect reciprocity, network reciprocity. So, or group selection is also, a social solution to the cooperation problem, and this will become important later. Multi-agent reinforcement learning, on the other side, coined this idea of sequential social dilemma. So that's really stopping from this very simplistic notion you can cooperate or defect, and says cooperation is not readily available as a single action. It must be learned over a sequence of actions. And so in a few years ago, this happened often in this grid world paradigm, having a more complex extended environment with the same game theoretic dilemma embedded underneath, and common solution approaches draw upon the vast amount of research in also other fields but other regarding preferences, having influence on others, norms and reputational contracts where have been applied successfully to get cooperation there going. So now that we have a vague idea where these two fields stand, how can we build bridges? And the first part is, okay, we want to realize, we want to focus on modeling for understanding. Yeah? So it's not about scaling. We keep that problem in the back of our minds, but for the moment, our goal is to understand things better. And then we need to be modest and say, okay, all models are wrong. There is no perfect model. And then the main conclusion of that is, let's treat multi-agent reinforcement learning as a nonlinear dynamic system. So what does this mean? So I think I'm thinking about this question for almost 10 years now. And only recently, I've come back to this Mars level of analysis in a refined form that I thought about in 2022, where the idea is that these learning dynamics sort of extend the process level analysis on a higher level. It's a more abstract level of analysis between the concrete process level that would be a traditional reinforcement learning algorithm and a traditional multi-agent reinforcement learning simulation, and sort of the goal level. What do I want to achieve? What is their reward function? What do they care about? What kind of game theoretic equilibrium concept I'm thinking about? And the way then to do that conceptually is sort of as a zero step, we use very low dimensional environments. A lot of the research is about making the environment as simple as possible, but not simpler. And you will see an example of that in a few minutes. And then regarding the learning dynamics, again, it's just realizing that a few weeks ago, that these three principles or three elements. So most of these dynamics are deterministic. So they reduce the stochasticity that is inherent in an algorithmic learning process and sort of just give you the mean dynamics or the average dynamics. And that has obviously advantages that you don't need to model and simulate all the noise and can focus sort of on the average direction. Then these dynamics typically reduce the dynamic state space. So if you have a learning algorithm that tracks sort of state action values, then most of these dynamics are reduced in a sort of directly in the strategy space. So they're also easier to handle. And the third element is the least paid attention and the most abstract one. I'd be happy to just talk about that, but as it's the most nerdy one, I'll just leave it for questions or discussions in the future. But basically, it's about what kind of feedback does the learning get, and that we want to reduce it, the asymmetry, because of our own play. So a bit abstract. But in a nutshell, okay, we have these three elements that we can go from MAR. And so for those of you who haven't worked in multi-agent reinforcement learning, the basic framework is you have agents and environment. The agents take actions and receive rewards and observations. And then in the standard reinforcement, multi-agent reinforcement learning loop, you can think of an interaction phase where they assess their reward prediction or temporal difference error, depending on the community you're in, which tells the agent how they should adapt, how they should change their action rule, their policy, their strategy, again, depending on the community you're in order to get more reward over time. And all of this is, of course, beautifully formalized. So we don't have to start from scratch. And with these three elements of reducing stochasticity, reducing the dynamic state space, the feedback asymmetry, we can sort of derive sort of learning equations. And this has relations, or the origin is in mathematical biology. Here, this is, you could call a discrete time softmax replicator equation or replicator dynamics. And this is, to me, sort of the modeling framework that gives me a transparent account of the dynamics of collective behavior emerging from the individual agencies in different environmental contexts, fitting between the three type of models. And all of that is not, falling out of the blue. It's really advancing on the shoulders of many giants that might not be aware of each other in one way or another. So you'll find flavors and influence of this learning dynamics approach in machine learning, in control and engineering mathematics, statistical mechanics, economics, sociology, and mathematical biology. And the challenge here is really that these different fields have slightly different goals, what they want to achieve with their work, and different ideas what the role of game theoretic equilibria are and how plausible they want their learning processes, learning dynamics to be. Some care about biological plausibility, others not at all. So let me walk you through a concrete example, what can you do with that? And the question we are asking here, how do natural tipping dynamics affect sustainable collective action? So what does this question entail? Why did we ask it? So the prevailing view in cooperation science, let's call it like that, is to achieve cooperation in a social dilemma, we need some form of explicit social interaction, such as different types of reciprocity, agreements, or just communication and behavioral experiments, or social norms. And social norms might be more implicit than reciprocity, but they are still, in my view, an explicit social phenomenon. And so I was wondering, did we overlook something if we focus on the social? Instead, can we ask, what is the cooperation promoting potential that stems solely from the fact that all decision makers are embedded in the same ecological environment? And I think that's a exemplary question that requires a model, because it would be very hard to isolate social interaction in an experimental approach. But within a model, we can do this relatively cleanly. So what do I mean with isolating the ecological interaction? So this is our minimal commons model with a tipping element. And this is also an example where you see stripping away from a choice environment as much as possible, but still having the ingredients that we care about. So in our simple model, two agents must decide between conserving the environment or choosing intensification. The environment models the supporting and regulating ecosystem services, so the indirect ones, and these are either functioning, the environment is prosperous, or degraded, not functioning. When the environment is prosperous, it delivers privatized provisioning services. So these are the direct services we get from nature, like agricultural harvests, timber, things like that. And this is parameterized with a short-term conservation incentive, delta R, between 0 and 1. And so although this looks here like a game matrix, it's actually not. Just at the prosperous state, see if agent 1 chooses conservation, it doesn't matter whether agent 2 chooses conservation or intensification. Agent 1 always gets delta R. And if they choose intensification, they get this normalized payoff of 1 for intensification. And so that's why the short-term conservation incentive is between 0 and 1. And let's say it's at 0.8, it would get 80% of the utility that compared to what they would get when they would intensify. Now, why might intensification be problematic? Yeah. Well, it can collapse the environment. It can destroy the supporting and regulating ecosystem services. And this we parameterized with a collapse leverage, QC, which is sort of a probability or time scale it takes from the prosperous to the degraded state. And the more agents choose intensification, the greater this risk is. And on the other side, if all choose to conserve, then we say, okay, they are guaranteed to be in the prosperous state. This guarantees safety. When they are degraded, they have received zero utility, so the environment is shared. That's the process. It's not individually. When the environment gets destroyed, everyone suffers. They get this zero utility at the degraded state and have to wait for a certain amount of time steps parameterized by the recovery probability, again, between 0 and 1. And the last bit is the agents care about the future with some degree parameterized by their discount factor. And this is just standard exponential discounting here with an infinite time horizon, as it's often done in economics and reinforcement learning. It's the same mechanism. What do we find? Despite that there is no explicit social interaction, here in an exemplary parameter space, we find all three social dilemma types here with the different colors, plus two harmony collective action regime. So the ecological dynamics can here act really as a catalyst of cooperation. It gives us the full range of social dilemmas and beyond. And moreover, the base likelihood. So if you take sort of an uninformed prior over the whole parameter space and just sample that linearly, the outcome is not at all equal distributed. So interestingly, over 75%, so 3 out of 4 instances, we are either in an intensification or a conservation harmony. So there we have no conflict of interest. They either want to go to intensification and are happy with that, or to conservation and are happy with that. And only under 25, so the rest are these collective action regimes that you would call a social dilemma, like a prisoner's dilemma, a chicken game, or a stack hunt game, to different degrees of likelihood. But it's below 14% that you have actually, this full tragedy of the commons as depicted by a prisoner's dilemma. So commons with tipping is not doomed to tragedy, which is why, I'm thinking about this might be actually a fixed rule for the emergence of cooperation, ecological reciprocity. Now, if we make the agents heterogeneous, more collective action regime emerge. And here the picture looks not so nice, or yeah, I would say not nice, because here just having the same type of analysis, but now with each agent gets their own independent sample of the 4 parameters, the discount factor, the short-term conservation conserve, the impact on the collapse, and the recovery probability. Then more than half are so-called, what we call the fixed chicken regime. So that is divided action and its inequality in the outcome evaluation. So heterogeneity leads to inequality quite substantially. Just taking the structure of the model. And if we sort of, despite the high abstraction of this model, map this to some empirical regime shifts used here from the regime shifts database, which is a very nice source of a mix of qualitative and quantitative data, we can still, I think, take away 2 takeaways. First of all, game theoretic considerations are relevant to the analysis of decision-making in ecological tipping elements, because these dots are the empirical tipping elements in their collapse and recovery timescale, and they span different incentive regimes. And interestingly, you know, around sort of an uncertain tragedy of the commons, the prisoner's dilemma bit. But, you know, I want to be cautious not to interpret too much into it, but at least having a game theoretic modeling approach seems relevant. And also, I think we can say that the ecological dynamics are critical here to the optimal decision making, and more refined models focusing on that particular question should take these into account. So now let's get back to the learning. This was sort of an equilibrium-based approach. The learning dynamics microfound all of these collective action regimes perfectly. So here you have a prisoner's dilemma, stack hunt, chicken, harmony. Then you have here the inequalities with cycling emerging. So this is sort of a perfect one-to-one correspondence. And now let's zoom in this stack hunt game regime, because there are some interesting phenomena can be discussed. So this is a coordination problem where they need to coordinate either on cooperation or defection. And the final outcome depends on the initial behavior of the collective. That's the idea of multi-stability. And basin of attraction is a dynamical systems word for saying, okay, which of these initial points lead me to one or the other point. And conceptual links you can make is to a measure of collective intelligence itself, here proposed by Naomi Leonard and Simon Levin. It is very much connected to the idea of social ecological resilience, which is also based upon a dynamical systems framework. But more computationally side, you can think of it as an emergent collective memory, because you know you can store one bit of information there in the collective, are we in one or the other regime. And it can also be a geometric view of ad hoc teamwork, in the sense, if I remove one agent, and let's say they are in this cooperative equilibrium, now if I enter one, but I don't know what their initial behavioral bias is, here I'm very much optimistic that regardless what they do, they would still relearn to cooperate. So, and we can directly see that at this dynamic phase space. Now, if we look into the time, how long it takes, and imagine we compare these two most adjacent bundles that started right at the boundary, the so-called separatrix, that agent learning appears almost as converged. You know, they seem almost converge on a medium level of cooperation. So imagine if you just had the view of time steps versus the level of cooperation, and then only if you let it run for long enough, they branch out again. So a very tiny change here at the beginning leads to a drastic outcome at the end, but on a very interesting transient dynamics. And so only if you're aware of that geometry, you can make sense and sort of simulate for long enough. Now, if we stay in that picture and now simulate all points, having agent one on all points on that orange line, and just track how long does it take until they converge, you see at this critical point where they cross the different basins of attraction, the convergence is up to an order of magnitude longer than when they are far away from it. So when you are at such a regime, convergence becomes less relevant. If you spend all the time learning, then you should deal with that process. And the focus is then on the transient, the time until convergence, which has some potential also to integrate some early warning indicators from complex system science that are about to detect, are we at a tipping point or close to a tipping point or not? And, you know, this might be some idea. These thoughts can influence also the algorithmic side. So far, we stayed at sort of a single point here in the blue regime, in the in the parameter space. Now, what this basic model tells us, we can actually change the incentive regimes just by changing some parameters that are either individual or ecological, no social interaction. So let's imagine we change the future care of the agents, so around 0.5 here, that we traverse the prisoner's dilemma to the coordination, to the stack hunt, up to the fully harmony game. The corresponding learning picture here is a no cooperation, a lot of cooperation, but interestingly, on the timing side, you have the same sort of conclusions as within a strategy space. When you at the transition, when you are in the transition regime, the time it takes to learn is much longer than when you are away from it. And the last sort of phenomena that is typical on the complex system side, but maybe less so on the algorithmic multi-agent reinforcement learning view is we also find hysteresis, so a form of collective memory, history dependence. So when the agents care for the future, so the discount factor rises and then falls again, the collective actually remembers the good regime here and then remains cooperative until another sort of tipping point is hit. And then this has two consequences. So when you are at such a regime change, the change is quite robust. So if you tipped here and then slightly go back, you still cooperate. That's wonderful. But this is also true for the negative side. If you are here and slightly go over, then this regime change cannot be undone by simply go back to the discount factor. You have to go all the way back to here that you can do the other change again. So depending on which way you go, yeah.
So a question about this, because I think a lot of these dynamics depend on exactly how you model learning. So this is obviously a game with some more notion of RL. So can you go deeper into like your model of learning from prior games or the RL component?
Yeah. So the learning is, imagine a very standard temporal difference learning framework in this deterministic fashion. So the agents basically compute their long-term expected value for each state action pair. And then they sort of assess for each state. So here for each, basically here in this environment, only the prosperous state is important, because in the degraded state, they cannot do anything. But still, they need to keep track of the states in order to be able to assess, okay, if we go degraded, it's going to be worse. And so just for the evaluation's sake, they need to be aware, okay, there is a degraded state. And then they say, okay, is it better now? So for example, here they are at a mixed strategy where agent 1 plays with 75% cooperation and agent 2 maybe with just 25. And so these errors that you see are actually the real temporal difference error. Let's say, okay, in which point on average does the learning dynamic want me to adapt? So here this means agent 2 actually wants to cooperate a bit more, but agent 1 feels exploited, right? They want to go to defection. And so this gives you then this curved dynamics in the strategy space.
Okay, and it sounds like there's one more dimension in the learning space where if this fails, then the arrows change across games.
So
it sounds like some of the parameters of the game change based on prior experiences.
so this state space was sort of one point in this blue parameter space. Now, when you change the external sort of, some call it hyperparameters of the model, here it would be okay of the choice environment, but okay, maybe we can see the discount factor is a hyperparameter of the agent. Then also, you know, the flow in the strategy space would change. And it's basically what we have here. Here you have these two equilibria, and if you move that stack hunt regime into a conservation harmony, then you would basically move this red line downwards until this defective or this intensification equilibrium is removed, gets eradicated. And then all arrows point to this conservation harmony. This how you can imagine these collective action regime changes.
Got it. Thank you very much.
You're very welcome, and I'm almost done. Just here again explaining a little bit how these pictures connect. So if you know, okay, this is the parameter space here on the left, then you're actually not surprised that this hysteresis happens because you transgress the coordination, the stack hunt regime, which has the two equilibria present. And only if you go from here, the stack hunt back to the prisoners, the cooperative equilibrium is gone, and then all the dynamics has to go back to the defective equilibrium. So to summarize, I think that could show, I mean, I hope could show why this analysis is useful, because at the pure algorithmic level, it's very difficult, if not at all possible, to define what you actually mean that you are converged to a strategy, because it's stochastic. We can analyze the different basins of attraction, the bifurcation. So this means when do equilibria come to in existence and when they stop existing, when you change external parameters, and also the timescales it takes to learn under different scenarios. This is possible with a dynamics framework and not really on the algorithmic level. So you can't do a bifurcation analysis on the level of a for loop. And the resulting geometry, like how these strategy spaces are shaped, is relatively robust. You know, I mean, this is of course an ongoing research field on its own, but sort of being on a higher level, you have many algorithmic instances that give you sort of the same flow, and also the picture integrating stochastic noise into it is sort of coherent. Yeah, it's not, you know, one-to-one, but sort of it makes sense. So the research program is something, you know, I want to invest into further. But at the same time, important, it's not just a new thing, you know, it's not connected at all. It is by sharing the same multi-agent reinforcement learning foundation that many researchers are researching, because they're interested in scalable algorithms, how to extend this to large, high-dimensional environments. You know, the hope is that these communities can continue to enrich each other and have a common ground, sort of to be same play field, and then, you know, there are different areas researched by different approaches, but they can always talk to each other. So let's conclude. Are we now smart enough for the good life? Well, we don't know yet, but I hope we have an approach how to answer that. So I started with why we need that, and collective action challenges in human ecologies are really not just about individual raw intelligence, but about the dynamics of how collectives learn together. How we can go about it concretely with this approach of collective learning dynamics, bridging complex system science and multi-agent reinforcement learning. opening up a new analysis level. And as a concrete case, I showed you that the environment is not just a passive backdrop of human cooperation, but an essential catalyst for its formation. When we ask, what is the cooperation promoting potential of being embedded in the same environment, removing purposely all the direct social interaction. And this, posits ecological reciprocity as a possible sixth rule for the emergence of cooperation. So the intelligence we need for the good life is collective, dynamic, and ecologically embedded. And we have a way to model it transparently. Thank you very much for your attention.
No, fantastic. Thank you very much. So a lot of the stuff obviously connects like classic games, game theory with RL. If you start connecting this to more, what's called the climate impact models, the global impact models for climate that combine climate, economics, and so on, is there a way of embedding some of this decision making into these impact models?
So I think that's an exciting application area. My view of that literature is that most of these are not game theoretic.
Right.
So that of course you could do also a non-game theoretic, a single agent model there, and have sort of a stylized sort of choice environment. You would basically need to translate the choices the social planner agent is faced with into a decision environment that is sort of low dimensional enough or stylized enough that it can work with that. And in order to have a meaningful analysis, of course, you would want to play with certain parameters there. The famous question is, how large are the damages because of future climate change? The sensitivity analysis aspect is sort of what this framework excels with. But then, of course, if I were to go about it and devise a research project, it would be game theoretic in nature. And there, of course, there are related works on more the climate impact modeling side that are game theoretic, but the field is less less so than single social planner agent, but the more reason maybe to look into that.
Okay, it makes sense. And then one other aspect of the real world that I think you mentioned is kind of like social norms, but I'm thinking still game theoretic, payoffs, communal payoffs. If we feel like we're in the same group, your benefit is my benefit. We feel like we're in different groups, the opposite, which in the real world, nations or ethnic groups or whatnot tend to have that dynamic. So how can you incorporate that as you bring this closer to applicability?
Yeah, so this is also an interesting avenue for future research. Social norms, I think, can be modeled in very different ways. If we go back to these mechanisms, the rules of cooperation, I would look into indirect reciprocity and group selection. I think what you talked about is a bit about, had a group selection idea, but also indirect reciprocity is connected to social norms, where the idea is, I don't know what you did, but I have some kind of assessment. Are you a good guy or a bad guy? And then one way to understand social norms is to have a rule. I cooperate with good guys or gals, but with the bad ones, I defect against them. But this might not always be the case. Maybe it's also good to cooperate with everyone. But is then this sort of norm, this rule with whom to cooperate, viable. So there is work in that, in evolutionary dynamics, and also, increasingly moving with a reinforcement learning frame. And with these learning dynamics, this reinforcement learning dynamics, I think mathematically, the way I would go about this to model is going into the direction of mean field games, where you obviously want to have the notion of a large enough crowd of agents, but to be tractable enough as a model, you start by thinking about or treating the majority of agents as identical, and then you have sort of a mean field of a focal agent. So that's the very high level idea of mean field games. And I feel and there is a connection there.
Yeah, and then if in that vein, it seems like agent-based models are complicated when you have thousands of millions of agents. But if there's a one mean field for every agent, that seems like a tractable way of approaching that. Is that a decent enough hybrid, especially when the agents do RL, like continue to do the other work?
Yeah, I mean, I think there are different positions to it. You don't do any sort of analytical approximations and just model your thousands of agents individually. And if you have enough compute, no worries, could do that. And sort of the most extreme is you assume everyone is identical and you have a nice mean field for everyone. And probably there's a middle ground there where my intuition is you sort of have an average or a mean field of the large population, but then you have a closed circle of interactions that you track more or less individually. So that might be some kind of a hybrid approach you were mentioning.
Yeah, excellent. That makes a lot of sense. Well, yeah, thank you very much. It was enlightening.
I'm glad to hear that. It was a nice experience and a nice opportunity to change my slides to this quarter presentation.